Hello everyone, welcome back to Let's Unbound. So yes, we are in the last part of AP Precalculus Unit 2, Concept Review plus Problem Solving, and it is 2.15 semilog plots. Yes, and this will be not the end, this is just the last part of the unit, but we will have an exam style problem solving video also. So that will be the next in this particular playlist. And yes, let's get into what is semi-log plots. So what is this log scale? Let's understand, because plotting, we need to understand scales. Usually we will do linear scale, right? But when your data values covers a very wide range, like 1,000, not just 1,000, like 10,000, million, kind of that, plotting them directly on a regular linear scale. Linear scale means like I will skip by fives, tens, right? In that way. So it's very hard to see the patterns. So that if we see the pattern, we might suggest it's a cubic or an exponential or a linear something. So the larger values will stretch your scale and making small values appear compressed. And almost in these cases, we will see the graph near the x-axis. Like we will zoom in, but we can't zoom that much. We will adjust the window settings, like in technically I'm telling, right? So yes, we need a solution, and that is logarithmic scale. Instead of plotting the raw values like 10,000 all those, we will plot their logarithms. And with base, basically we can take suggested base or general common logarithm with base 10 we can pick, right? So let's see how this log scale works. So here I have some values. X1 is 1, 2, 3, 4, 5. And Y1 is, the range is becoming 20, 200. Okay, that's fine. Then 3,000, 52,000, 250,000, right? So I need to adjust my window system. Like my scale goes like this. Now, if I ask what point is this, it seems like 0, but it's not. It's 200. So that's the problem. I need some different scale. The linear is not enough here. Okay, the problem is with the range of values. So we will work on it, right? So there I will take the logarithm of y1. Okay, that will give you some simple values. So one will be linear and the other will be based on logarithm. So this is what semi-log plots. It's not fully logarithm, right? One is linear, other is logarithm, is semi-log plot. Here you see, I just take log 10, log with base 10 of the y1. And I got this. So very simple. But I see a pattern of straight line over here, right? Previously, before log, I see a pattern of an exponential. Yes. So in general scale is exponential, and here it is in semi-log. It is this, right? So this is ln of y, and this is x. Correct? Sorry, not ln. It's log y. So this is semi-log plot, right? So why we should always consider on y-axis and how actually it is, right? So it's the linear scale, like it's 1, 2, 3, 4. Like if it's 1, like 5, in that way we can do like 5, 10, 15, like any normal scaling adding up. But how the logarithmic scale on y-axis will work? So 1 to 10, I hope you can see this. So there is a line like this. Okay, between 1 to 10, it's not evenly divided, but it's divided something like this. Okay, so let me draw this. And this is how the logarithmic gaps will be equally, not equally spaced, they will be spaced like this. Okay, so 0 to 10, you will have, like it is getting closer and closer. Like I mean 1 to 10. So 1 to 10, each line is 1. So this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and 10. Then 10 to 100, if you go to 10 to 100, let me show you. 10 to 100, it will go like 20, 30, 40, 50, 60, 70, 80, 90, 100. And 100 to 1000, it will go like 200. In hundreds, it will get multiplied. So this is how the logarithmic plotting will be done. Okay, it's not an equal spacing like linear. So a semilog plot is where one axis, usually y-axis, is on logarithmic scale, and this is how we should space them, while the other axis remains linear. Okay, so 0, 1, 2, 3, 4, 5 in that way. So it's simple adding. But this, it behaves differently from 1 to 10, 10 to 100, and 100 to 1000. Likewise, it will go on and on. Right? Now, moving to question. A scientist studies the growth of bacterial colony. The population measured every hour is shown below. Time and population. The scientists think the population grows exponentially. Test the hypothesis using a semi-log plot. Okay, so you understand one thing. We see one example. So in a linear, in our normal plotting, exponential will something look like this, exponential, right? But how it will look in semi-log plot, we are going to test the hypothesis. He thinks that it grows exponentially. So in semi-log plot, it should represent a straight line, right? So let's go with that. Let's see how to solve. And yeah, many parts are there. Let's do one by one. First, testing the hypothesis. He thinks it is it grows exponentially, right? So P of t, I'm just initial, like general exponential model function I'm writing, e power some k, the growth factor, and it depends upon time, right? Now, how can I use, so you just go to the Desmos and make a linear regression, right? So now, let's see. Let me go to Desmos and show you. Okay. So you have to give your values as usual. So give the table and what will the table values given to us, right? So I have 0, 1, 2, 3, 4. Okay, and y values 150, 225, 330, 337.5, 506.25, 759.375. So do this clearly. And yes, here you see the problem. We can't see it. So we will adjust the window. But let me take ln of this y1 or log y1. You can see this, right? So this is a semi-log plot, what I can see here. So it represents, what is it? It's a straight line, but in a semi-log plot, if it's a straight line, in actual plot, it will be an exponential. Okay. Let me show you this. That exponential, we need to adjust the window setting. So y is a problem. So x is from 0 to something 7 I'm giving. And y you should adjust its minimum. Okay, let's go from 0 to maximum is 800 I'm going. Right, and step you can give maybe 50s or hundreds if I give. Okay, like this I should adjust. And can you see an exponential way? This is in a regular form, right? For a clear structure, I just use log of that. And yeah, so semi-log plot had shown me a straight line. Okay, it's like this, but I need to adjust the window again, right? So right, this is the hypothesis is true. So he is correct that it is kind of exponential. So the first the testing the hypothesis we did, and let's write the answer. Okay. So now how I did it from Desmos, like what if it's non-calculated? So if it's if in a regular plot, if it's exponential, like he thinks it's exponential, then it's semi-log plot. Semi-log means what? Your y will be ln, your x will be x. So your points will be something like this, right? So now let me, okay, if it's exponential, then you convert to log and it should give you a linear equation. Okay, this is exponential in regular, linear. So now let me take ln on both sides. Ln p of t equal to ln p naught e power kt. Okay, so the ln is in multiplication, so I can split it ln P naught plus ln e power kt. Ln and e are reciprocal to each other, so I will get ln P naught plus kt and ln P of t. Okay, so ln P of t is your y, like if t is your x, right? And ln P of t. So this is how this function, this context, the function model looks like. So y equal to, this is a slope and x plus c. So yes, he thinks it is exponential and I convert to the semilog plot, right? So because your x value is the real, like a normal linear number and y is in logarithmic form. So yeah, it represents a straight line when, yes, semilog will linearize your exponential equation and hence our hypothesis is the testing hypothesis over. And yes, if growth is exponential, plotting ln P of t versus t should give you straight line. And yes, we got a straight line. In this way, we tested the hypothesis and it is correct. What he thinks was correct, right? We can also see that in graphical form, right? So that's it. Now, find an exponential model P of t that fits the data. So exponential model, like we can use calculator, like regression, or we can do it using this also because we have table of values, right? So P of t equal to P naught e power kt. Now, there is an initial condition given in table of values, which is 0 is 150 and 1 is some simpler numbers I will pick. I'm going to pick these two to make my function, right? I hope you can remember this when we did this in what we say, exponential functions, right? So P of t, like when t is 0, your P of, like this is 100. P of t is 100. I mean, it's 150. So what does it means? P naught is 100. So 150 equal to P naught e power 0k. E power 0 is 1. So P naught equal to 150. Right? So I got, when you find k, the model will be complete. So you pick another point. So 225 equal to P naught is 150. E power k is, we don't know, t is 1. So 225 by 150 equal to e power k. And I want k, right? So I'm going to take ln on both sides. So ln 225 by 150 is k. You can keep it as it is, or you can convert to a, like approximate to a decimal, right? So you will get approximately 0.4055. Okay, so my model will be P of t is 150 e power 0.4055 t. This is my exponential model that fits this data, right? And getting into the next part, see. Interpret the slope and the intercept on the semilog plot. So in a semilog plot, we did this right while testing the hypothesis. Ln P of t equal to ln, what we got? Ln P naught plus kt. So now I know what is P naught and kt. So ln P of t equal to ln P naught is 150 plus k is 0.4055 approximately and t. Now interpret the slope. What is slope here? If this is y equal to mx plus c form. So slope is k equal to 0.4055. Right? So what does it say? It's a positive thing. So it will tell how fast, here we are talking about the bacterial growth, right? How fast the population grows per unit time. That is what the slope means. So how fast population grows per unit time on logarithmic scale. Okay, so that's important. We are interpreting in this form. So what is this? When it is a larger slope, there will be a faster exponential growth, right? So, okay, so what we can see here is 0.4055 and okay. In this case, like how the population will be calculated, P of t is initial population e power kt, like 0.4055 and t. So this will approximately give you the z power 0.4055 will approximately give you 1.5. So 1.5 means what's the OG1 whole and 0.5, 50% growth per hour. Okay. So this is the interpretation. 50% growth, approximately it is. Okay, approximately 50% growth per hour in this bacterial colony. Right. And coming to, let's do this part here, y-intercept, right? Let me make this smaller, right? And y-interpretation, that is intercept. Intercept means y-intercept. And this ln P naught is y-intercept, that is ln 50. Ln, I mean 150 is the y-intercept. It is approximately 5.01, right? So this is the value. What does it mean? It's very simple. E power, like in this, like what does it say? It says initial population, correct? So P naught. So in population term, e power your intercept, right? E power, because we write P naught e power kt. And when your intercept comes here, it will give you the initial population. Like ln 150 is approximately 5.01. Means 150 is approximately e power 5.0. So exponential. Based on the log scale, right? So the intercept represents the starting size of the bacterial colony. Intercept, it represents starting size. In regular day, you will say 150 is the starting size, right? But in this scale, log scale, this intercept will 5.0, ln 150, 5.01. That is the starting size of bacterial colony. Right? So that's it. And now let's move into T part, compute the doubling time. So what is doubling time? So doubling time is initially I have 150, when it will become 300. Okay, that time is doubling time. So very simple. So we have this simple. Population of TD, doubling time is equal to 2 times of initial population. Right? So this I need 2 times P naught, and P of TD I can write it P naught, like I'm writing this, e power K and the doubling time. So P naught will get cancelled, 2 equal to e power KT. And we need to simplify this. We will get ln 2 equal to, when I take ln on both sides, ln e power KTD, ln this cancel, ln 2 is KT. So your TD is, like, I mean the doubling time is ln 2 by K, right? So, and we know the K value, so TD equal to ln 2 divided by K is something we read 0.4055, and we can simplify this doubling time, and we will get approximately 1.709. So after 1.7 hours, the bacteria colony will have a double the population than the initial. Right? And this completes the problem 1. Now getting into the question 2. The histogram below shows the population of 15 cities in number of people plotted on a logarithmic scale. How many cities have population between 100,000 to 1,000? So how logarithmic scale will be done? Right? So if it's one histogram bins are like 3 to 4, 4 to 5, right? So how many cities has this population? This is log of city population. This y-axis says number. Okay. So when I say, okay, I want to find this. So 10 power 5 and 10 power 6. So I need to look between 5 to 6, and this represents the number of cities. Okay. So there are 7 cities which has the population, this 100,000 to 1 million. Okay. That's simple. So the 7 cities is the answer. And in the same question, if they're asking for 1,000 to 10,000 people, how many cities? 1, because 10 power 3, 10 power 4, right? So 3 to 4 is not linear in logarithmic way because they mention it's plotted on a logarithmic scale. So we should take that as a 10 power, right? So if base is not given, you can take the common base 10. Right, and that's simple. Question 2. Now question 3. The table gives values of a function f for selected values of m. Which of the following graph could represent these data in semi-log plot? Vertical axis logarithmic. Okay, so it's linear. So this is first option you can see, it's 100, 200, 300. Linear, right? So it's a represent exponential. So in your semi-log, this should represent maybe a straight line. So what about this? This 0.1, 10 power 1. You can write 10 power negative 1, 10 square, 10 cube. This is multiplicating, right? It's not adding. Adding means linear. So this represents this log, but I want vertical to be log. So it's not. And coming here, this is spaced in a linear manner. This is like 10 square, like 10 power 1, 10 square, 10 cube. Vertical is logarithmic. So this is the required semi-log plot for this. Okay. And that's simple. Question number 3. And that's simple. The topic semi-log plots. I hope this video might be helpful. And yes, I have a bonus question to you. Take a screenshot and solve this and send your answers in the comment section. And with this, we are wrapping the video for today. Yes, I will be coming up with another video. So units and subunits are completely covered. The next video will be exam style problem solving on exponential and logarithmic functions. So stay tuned. Save the playlist for future reference. Also share it with your friends if you found this helpful. And let's meet in next video very soon. Until then, keep learning, keep practicing, stay curious.